10 seconds, you will leave Earth behind for what might be the last time you ever feel normal again. Not because the rocket explodes, not because anything goes wrong out there in the vacuum of space, because everything goes right, and that's exactly the problem. In 2019, NASA ran an experiment that changed how we think about this. They sent astronaut Scott Kelly to space for a year while his identical twin brother Mark stayed on Earth. Same DNA, same starting body. When Scott came home, his genes were expressing themselves differently than his brother's. His DNA had changed. Some of those changes never fully reversed. That was after 1 year, in low orbit, just 400 kilometers up, with a rescue ship always on standby. A Mars mission is 3 years, 225 million kilometers from any rescue. And the body that lands on Mars will face damage NASA's own data says we don't yet know how to undo. This is not science fiction. This is where NASA's own research is already pointing. Forget the radiation storms outside, the freezing nights, the thin red dust. The thing that ends this mission isn't out there. It's inside you. Right now in your bones, in your blood, in your own DNA, a countdown just as real as the one on this launch pad has already started. And unlike a machine, nothing can override it. Imagine signing up for a trip and not finding out the real length of it until after you've already launched. Here's the timeline nobody puts in the brochure. Earth and Mars only line up for an efficient launch once every 26 months. Miss that window, you wait 2 more years. So this isn't a trip, it's a sentence. 6 to 9 months locked in a tin can just to get there. Then over a year stranded on the surface. Then, maybe 6 to 9 more months getting back. Call it 3 years minimum, cut off from Earth, with a radio delay so long that a real conversation home is physically impossible. 3 years. One body, 4 ways it can fail. First, your bones start dissolving from the inside, the moment gravity disappears. Second, invisible radiation starts rewriting your DNA, cell by cell, and you won't feel a thing. Third, your heart, the muscle keeping you alive, starts shrinking, quietly, for years, until it's no longer strong enough to do its job back home. And fourth, your own eyes. The windows you're seeing this through right now start changing shape, blurring a future you may never fully see clearly again. One of those alone would be a serious problem. All 4, happening at once for 3 years straight, is why a growing number of doctors no longer think of a Mars mission as survivable in the way we imagine it. Let's go through exactly what happens, starting with the part of you that holds everything else up. Imagine your own skeleton, the thing keeping you upright right now, quietly turning against you, 1 month at a time. Now to the part of this story that should genuinely worry you. Your skeleton is not a fixed structure, it's constantly rebuilding itself, and that rebuilding depends entirely on gravity pressing down on it with every step you take. Remove that pressure, and your body doesn't just pause construction. It starts actively tearing your skeleton down because it interprets the lack of load as a signal that the bone is no longer needed. You'll lose roughly 1 to 1.5% of bone density in your weight-bearing bones for every month spent in microgravity. You're not in microgravity for weeks. You're in it for 6 to 9 months just to get there. Then, living under only about 1/3 of Earth's gravity on the surface, which research suggests still isn't enough load to stop the bleeding. A peer-reviewed model projected that nearly 2/3 of astronauts on a shorter Mars trajectory will develop clinically significant bone loss. And on the longer trajectory, the model predicts essentially the entire crew will. That means you. This isn't a bit weaker. This is the skeleton of an elderly osteoporosis patient built inside your healthy 30-something body in under 3 years. Your bones will be thin enough that a fall that would just bruise you on Earth could fracture your hip on Mars. And the damage doesn't reverse on a timeline anyone would call quick. Astronauts returning from 6-month stays on the International Space Station, a fraction of a Mars mission's length, often need months of rehabilitation just to walk normally again. And some never fully recover their original bone density at all. And some never fully recover their original bone density at all. And here's the part nobody likes to think about. The same skeleton that's quietly disintegrating inside you is the one that has to survive the launch back to Earth, the G-forces of ascent, the jolt of re-entry, and then has to support your full body weight again under Earth's gravity for the first time in years. A skeleton that's lost a third of its strength doesn't get a warning before it fails. It just fails. At the worst possible moment, imagine an enemy you can't see, can't feel, and can't stop, working through every cell in your body for 3 straight years. While your skeleton is breaking down on the outside, something even more dangerous is happening on the inside, at the level of individual cells. On Earth, our atmosphere and magnetic field absorb the vast majority of cosmic radiation before it ever reaches us. The moment you leave that shield behind, every cell in your body becomes a target. This isn't ordinary radiation. It's high-energy cosmic rays capable of tearing through your DNA strands directly. NASA's actual radiation sensor, flown to Mars aboard the Curiosity rover, measured the dose for a 6-month transit alone at roughly 340 millisieverts. Double that for the trip home, and the round-trip transit alone adds up to around 660 millisieverts hitting your body before a single day is spent on the surface. Add a 500-day stay on Mars, and your total exposure pushes past 1 full sievert. To put that number in perspective, that's roughly equivalent to a full-body CT scan every 5 to 6 days for the entire length of your mission. It's also more than the career radiation limit NASA sets for its astronauts for their entire working life, used up in a single trip. And on top of that, the European Space Agency has stated plainly that you could absorb radiation doses up to 700 times higher than what you'd experience on Earth. Risk models estimate that this exposure carries somewhere between a 5 and 20% chance of contributing to a fatal or life-altering illness for you. A number high enough that it factors directly into mission approval decisions. Imagine knowing that simply making the trip carries roughly the same odds as a single unlucky round in a game of Russian roulette, with 5 to 20 chambers loaded. Except you can't see the gun. You can't feel it firing, and the damage might not surface for years, and there's no way to shield against it. Thicker walls don't solve the problem. At these energies, shielding can actually make things worse, shattering incoming particles into a spray of secondary radiation inside the spacecraft itself. So you absorb this dose silently, for years, with damage accumulating in places you can't feel. Bone marrow, blood vessels, brain tissue. Damage that may not show symptoms until long after the mission technically succeeded. Imagine the one organ keeping your brain alive, slowly getting weaker for years without you ever feeling it happen. And then there's the organ everything else depends on, your heart. On Earth, your heart works constantly against gravity, pushing blood upward to your brain. It's a muscle, and like any muscle, it only stays strong if it has to work. In space, that resistance disappears, and your heart, like your bones, starts to shrink. Studies of long-duration astronauts have recorded heart muscle mass dropping by as much as a fifth over an extended mission, alongside a measurable drop in total blood volume, as fluid that used to fight gravity simply redistributes and gets flushed from the body. It's a heart that's been quietly retrained for a planet with less gravity than the one it has to come home to. Like an athlete who stops training for years and is then expected to compete at full intensity on day one. Except the competition is staying conscious during a high-G re-entry. That's the cruel irony hiding inside the whole mission. The exact bodily changes that let you survive comfortably on Mars, lighter bones, a smaller heart, less muscle mass needed for a lower gravity world, are the same changes that make surviving a return to Earth's gravity genuinely dangerous. Your body doesn't get to choose which planet it adapts to. It just adapts to whichever one it's currently standing on, and after years on Mars, the body you've built is a Martian body being asked to come home to a planet it's no longer built for. Imagine looking at the world through your own eyes and slowly not being able to trust what you see. And there's one more change happening, somewhere you'd never think to check. Your eyes. In weightlessness, fluid that gravity would normally pull down toward your legs instead drifts upward, pooling around your head and behind your eyes. NASA's own data shows that around 70% of astronauts on long missions develop some form of swelling at the back of the eye. The optic nerve pushed and squeezed by pressure. It was never designed to handle. The back of the eyeball can actually flatten, like a ball slowly losing its shape, permanently bending the surface you see the world through. Doctors gave this condition a name: spaceflight-associated neuroocular syndrome. In plain terms, your skull is quietly swelling and your eyes are caught in the middle of it. Some astronauts come home needing reading glasses for the first time in their life. Others develop changes that fundoscope exams can still detect years later. Is not the body that left Earth. Which is why, more and more, space physicians are quietly preparing for a possibility most people haven't considered. The first humans on Mars may not be explorers in the way we usually picture them. They may be the first permanent residents of another world. Not because they chose to stay, but because the body that made the trip there may simply no longer be capable of making the trip back. Imagine being remembered, not as the first person to walk on Mars, but as the first person who never had a choice to leave it. Getting to Mars was always going to be the achievable part. Leaving it again in one piece might be the part you were never actually built for. So here's the real question. If you knew all of this going in, knowing your own body would be the thing standing between you and home, would you still get on that rocket? Let me know down in the comments. I genuinely want to know where you land on this. If this kept you watching until the very end, that's exactly the kind of curiosity this channel is built for. Hit subscribe so you don't miss what we uncover next. Drop a like if your mind is still processing what you just heard. And share this with the one person you know who'd argue they'd go anyway. I'll see you in the next one.